Hi there, this is Penelope. This is the first of two short videos, just giving you some extra stuff, extra material on eigenvalues and eigenvectors. If we've got a square matrix, this is the whole thing about eigenvalues and eigenvectors. If we've got a square matrix, do we have a scalar, which is just a number, such that A times Y is equal to lambda times Y? And if we do, then we say that lambda is an eigenvalue of A, and Y is the associated eigenvector. Now, if we've got the situation where AY equals Y, then obviously the eigenvalue is 1. But if we want to find any other possible ones, what we then have to do is we need to solve, and we can, to make it all work, we can say that that's lambda times the identity, and then further rearrange it. Then we've got that A minus lambda I times Y, missed the Y, equals 0. Now, what we need to go a little bit further, and this is covered in class, is that a non-trivial solution for Y exists if the matrix A minus lambda I is singular. In other words, what we need to look at is that the determinant, because that's the thing about being singular, is that the determinant equals 0. And then the values of lambda that satisfy that are the eigenvalues of A. Now we then get a polynomial, as you'll see once we do a couple of bigger examples. We get a polynomial of degree n, and n is how many rows and columns there are in A, and you'll get n distinct solutions or n distinct eigenvalues. Now, it's really interesting. Eigenvalues of a matrix contain an amazing amount of information about the matrix. For example, the products of all the eigenvalues give us the determinant. If a matrix is symmetric, then all its eigenvalues will be real. Okay, so let's have a look at the one that we've got here. The eigenvalues are given by the solutions to that was my dog barking, not anybody screaming. Door is now shut on my study. Okay, so the eigenvalues are given by so we have to find the determinant of -1, 2, 2, -4 minus lambda times I, and that's got to be 0. So what we've got is then, if we do all that subtraction, so we're finding the determinant of that. Okay, that, when we find that determinant, is -1 minus lambda times -4 minus lambda minus 2 times 2 equals 0. So playing around with that, we get lambda times 5 plus lambda equals 0. So lambda equals 0 or -5. And if we needed to, then we can find that the determinant is of A is 0 times -5, which is 0. So that means that we can't find its inverse. Now that's just a really simple example, but it doesn't illustrate the idea. Now we'll do something that's a little bit more grunty, a little bit more useful. So we've got this thing that we call the characteristic equation of A minus lambda I has got to equal 0. So in this case, we can skip to doing it as 2 minus lambda 0, 1, -1, and then 4 minus lambda, and then -1, and then -1, 2, and 0 minus lambda. And that's got to equal 0. So finding the determinant of that, let's hope I can get it right without making any errors. First time, 2, 3. So 2 minus lambda times 4 minus lambda times -lambda minus 2 times -1 plus, now the next term is going to be 0, so I'm not going to put it in, but it will be 1 times -1 times 2 minus, that's my other dog barking, -1 times -4 minus lambda. Worse than children, I'm busy. And that's got to equal 0. Now this just kind of works out. What's left in the first bracket would be lambda squared minus 4 lambda plus 2. And then the second term becomes 2 minus lambda. We're still looking for where that's equal to 0. And putting that all together, we get lambda squared minus 4 lambda plus 3 equals 0. Now we can factorize that, and what we've got in the second bracket is a quadratic, which just happens to factorize. So now we have that lambda is equal to 1, 2, or 3. So these are our eigenvalues, but now we need to find the eigenvectors, so that probably should have been in there as well. Right, I'm going to need a bit more space. Whoops, a bit more space. Okay, 4 lambda equals 1. What we do is we put that into what we had before, and instead of lambda, now we're going to put in 1. So it'll be 1, 0, -1, -1, 3, -1, -1, 2, -1. And remember, this is now times x, but x is made up of x1, x2, and x3, and that's got to equal 0, 0, 0. Okay, from the first line, if we multiply that out, we can get that, oops, that should be a positive 1. From the first line, we can get that x1 plus x3 equals 0, and that'll give us that x3 equals -x1, that's fine. And from the third line, we can get that -x1 plus 2x2 minus, now it would be plus, it'd be minus x3, but we know that x3 is equal to -x1, so it would be minus x1 equals 0. So we've got then that all that's left is that x2 is equal to 0. Now that allows us to write that x1 is, all we have to do is keep them in proportion. So if x1 is, if the first one is 1, then x2 we've got as 0, and x3 just has to be the opposite of the first one. So it could be any number times that. If lambda equals 2, then we put lambda equals 2 into that expression and we get 0, 0, 1, negative 1, 2, negative 1, negative 1, 2, negative 2. And from the first line, we get that 0 times x1 plus 0 times x2 plus x3 equals 0. So x3 equals 0. One moment. And then putting that in the second one, negative x1 plus 2x2 minus x3 equals 0. So from that we can see that 2x2 minus x1 equals 0. That shows the way that x2 and x1 are related. So an eigenvector that corresponds to lambda is equal to 2 is that 2, 1, 0. Or it could be some number times that. So this is only an eigenvector that corresponds to that. And similarly, if lambda, given that the third version of lambda is 3, then we can do the same analysis to find that x3 is 1, 2, 1. So we've found the solutions for what we set out to find.